Hello and welcome to episode 85 of the HamCorp training manual. In this episode, we set up the Waterline up to and including grade 3. I hope you're ready for some math this episode because there is some optimization to calculate to minimize the EU cost of water purification. Given a constant power, minimizing the EU cost also maximizes the rate of water purification. Now, the way the Waterline works is there is a water purification plant. This is kind of a brain for an extremely large modular multi-block. At least that's how I'm thinking about it. Wherever I place this, everything else needs to be placed within 32 blocks. And the first thing I'm going to be placing is the clarifier. So the clarifier looks like this. It's an 11 by 11 kind of circle, and it just needs to go within 32 blocks of the water purification plant. So I made a little platform here. I don't know how big this is going to be, so I'm hesitant to put up walls at the moment. I'll put them up after I'm actually done building the whole thing. And 32 blocks is 2 chunks, so I've kind of approximately tried to adhere to that. So if I put a controller block here, I'll be able to place multis within this whole bit platform, and a little bit that way. This way is wasted space, of course, because of the solar towers taking up the space. So really I should be putting the water purification thing like here, or maybe even one chunk over. But I imagine I'm going to be refactoring things pretty often with this. So I'm just going to put it down here for now, and then I'll also put the clarifier maybe here. Clarifier done. I will say though, these optional tasks are not accurate. I didn't need this many iridium frames. I'm pretty sure for the water purification plant also these numbers were not right, but whatever. I think it's cool that I need to place the source blocks, the water source blocks in myself, but it is kind of hard to see which shader's on. Now if you look at the top of the screen, it says that it's unlinked, and you may notice that there is no energy hatch on this multi-block. That's because it gets its energy from this one. This does need to be powered. I have to build a cable, but to link the two, I need a data stick. I need to left click this and right click this. And that links it. Now it says link to purification plant. So I'm going to plug this in to my power, and then I'm going to figure out how this works, and then I'll explain it. I think the first step is pretty straightforward. All right, I have the clarifier going. I figured it out. It's pretty simple, like I expected. I swapped out the input hatch for a reservoir hatch because the input is, water. As a reminder for the recipe, it looks like this. So we need to supply activated carbon filter meshes, and there's a chance that it gets destroyed when it's being used, and you get the filtered water grade 1 out. And these side products I don't care about, like who cares about sticks, gold nuggets, and stone dust. I have an export bus for activated carbon filter meshes. My output bus here simply leads to a trash can. That's not strictly necessary, to be honest, because the clarifier purification unit has voiding mode on for everything, which is a bit annoying, because when this output hatch is full, I need this to shut everything off. But I will say, this 55 buckets of filtered water took a long time. So if I just put a super tank here, I'm good for a while. But yeah, here we go. Filtered water grade 1. This can be used in a bunch of different laser engraver recipes. To be honest, I don't think it's worth it in any of them because the EU cost of making this filtered water is much larger than the discount you get for using it. So unless speed is a really big issue for you, I don't think it's justified. I have already taken the cell and scanned it to make the Ozonation purification unit. This is one of the few crafts that needs more than 10 input buses. This needs 13, so I had to expand my assembly line by 3, and now it's kind of running out of space, which is a bit of an issue for the next really big craft I need to do. But that's a problem for future me. I do have the Ozonation purification unit now, And now the waterline gets a bit more complicated. Because the thing with ozonation is the way it works is you have your filtered water grade 1, which remember is very energy expensive to make. And you can combine this with ozone in varying amounts for a varying success chance. And there is a bit of optimization to do here because the ozone grows exponentially. Each one of these pages doubles the amount of ozone you use, but the success chance only grows linearly. So at face value, you would think, here I have 128 kiloliters of ozone and a 20% success chance. If I double that, I do double the ozone and I get double the success chance. So that's just objectively better because you're doing more and you're using less filtered water. But now it gets a little harder to see what the optimal route is because you double the ozone again. So now you're using 4 times the original amount, but you're only getting 3 times the success chance. But you're also using less filtered water grade 1. And of course, you can double it one more time for 8 times the original ozone and 4 times the success chance. And again, less filtered water being used. So it's not immediately obvious to me what the best amount of ozone to use is. So let's figure that out. I hope you're ready for some math. Before we get into the math though, I will say that to make ozone, it's simply air in the laser engraver. And I will be using the hyper intensity laser engraver because it's 250% faster and uses 80% of the EU normally required. The 250% faster is secretly an EU discount because if it's running faster at the same voltage, it's not using as much energy. Okay, math time. So what I'm optimizing for here is the amount of energy used per grade 2 water, which means I need to figure out an EU cost equivalent of 1,000 liters of filtered water, as well as for my ozone. So let's start with the filtered water. This is the recipe for 900 liters of filtered water with a 70% success chance. So here I have a table of my variable definitions. So T sub n is the total EU cost for one cycle of a grade n recipe. So for grade 1, this is the total EU cost of running the grade 1 cycle once, which is 73,728,000 EU. E sub n is the EU per liter of grade n water. So this is kind of what we're looking for. This is just a number that equates the amount of water we make to just the amount of energy that went into making it. So to make 1 liter of grade n water, we use E sub 1 amount of EU. P sub n is the probability of success for the grade n water recipe. So for the very first step, for grade 1, the success chance is just a flat 70%. So P sub 1 is 0.7. So here in section 1, I've got the stuff for grade 1 water. This is the equation that tells you how much energy goes into 1 liter of grade 1 water. And you can see that because this is the total energy divided by the expected amount of grade 1 water. And this works out to about 117 kilo EU for 1 liter of grade 1 water. So now we know what the filtered water grade 1 is worth in terms of energy. We need to now figure out how much the ozone is worth in terms of energy. So this is the recipe for making ozone. And also I need to consider that the high intensity laser engraver gives me discounts. After that, using the success chance, I can figure out what the different EU per liter values are going to be for these 4 different recipe variations. And then we can pick the best one for making ozonated water. So for grade 2 water, there are a choice of 4 recipes, and I've parameterized those using a new variable n. And this is basically just an integer that goes from 0 to 3. So n equals 0 corresponds to the recipe where we only get a 20% chance of success, and n equals 3 is the one where we have an 80% chance of success. And this is how the amount of ozone that we use scales. It doubles with each increase in n. So the 80% chance success one uses 128,000 times 8, which is 1,024,000 liters of ozone. Here I have the EU per liter for ozone. To be honest, I'm not 100% sure this is correct. So if I am wrong, please let me know. But this is my understanding of how the hyper-intensity laser engraver works. You get the 80% discount, and it works 250% faster. So 250% plus the base speed, so 3.5. And this works out to 70-ish EU per liter of ozone. And then finally, the EU per liter for grade 2. Let me just add that. The EU per liter for grade 2 water is given by this, which is very similar to the one above, actually, but it's not so obvious, maybe. So this is just the total energy that goes in divided by the expected amount of water. So the total energy that goes in is the base cost of the recipe itself, plus the EU equivalent of the grade 1 water that goes in. So we put in 1,000 liters, and the energy per liter is this much. And then the EU cost of the ozone. So this is the EU per liter of ozone, and A sub n is the amount of ozone. And I divide that by the expected amount of grade 2 water from this recipe. And the graph looks kind of like this. The negative numbers obviously don't mean anything. Basically, everything that is outside the range of 0 to 3 is meaningless because they're not options for the recipe. So really, this is just improving with the amount of ozone that we use. And it reaches the cheapest EU per liter value at n equals 3. And that means I need to use recipe 4 according to NEI. And that is this one. So the one that uses 1,024,000 liters of ozone. It's a bit weird because you look at this and at face value, it's like, oh, I'm using 8 times the ozone for only 4 times the success chance. Surely one of the others is better, probably this one. But no, the filtered water savings alone makes it worth it. So this is the recipe we're going for. Well, let me put together the ozonation unit. Where to put? Maybe here. One very important thing about the ozonation purification unit is this thing explodes if the input hatch contains more than 1,024,000 ozone gas. However, the ZPM input hatch has a capacity of exactly that. So this will never explode. I also checked how fast I can make ozone in a hyperintensity laser engraver. And unfortunately, it's just slightly not fast enough to keep up with this. So I'm going to actually have to make 2 of them to keep up with this. It's so close. It makes 960,000 per water filtration cycle, but I need just a little bit more. So I do need to make 2 hyperintensity laser engravers. After that, I will start routing the grade 1 water over to the input hatch here, and then we can start making grade 2 water. And then we can go into grade 3. And I think that is going to be quite complicated. I'll be right back with those laser engravers. Here is my double laser engraver setup with a bunch of air intake hatches. I actually do need that many to keep up. It's 8 on each one. Now this makes ozone, which I store in the super tank, and I have a pump feeding into a dual interface. I have a storage bus on the input hatch of the ozonation unit with a sticky card in it, so the ozone can only go here. And I've made a similar setup for grade 1 filtered water. And I turned this output hatch into an ME output hatch. Let's see if this works. In 2 minutes, if everything has gone correctly, I will have... Uh-oh. Not a strong start. Oh, I didn't link it. I'm a dumbass. Alright. Now this has been linked, and on the next cycle, we should get our first batch of grade 2 water. That completes the LUV section of the waterline, and now we can get to flocculation and beyond in ZPM. Looking at the recipe here for the flocculation purification unit, I don't think there's anything particularly crazy. So once I have my grade 2 water to scan, I should be able to do this. Grade 3 water. This is where I'm going to end for this episode. I've also considered grade 4 water. It's pretty simple, so I'll quickly go over it, but I'm not actually going to implement this episode. For grade 3 water, the success chance depends on how much polyaluminium chloride you put into the machine during the operation cycle. And you need to put in a multiple of 100,000 liters. If you supply an amount that is not a multiple, there's a penalty. So I'm just going to assume that we are supplying an exact amount that works. And the polyaluminium chloride is also fully recycled. So you get this flocculation waste liquid, which you can turn back into polyaluminium chloride. And I calculated how much EU per liter it costs to do that. And that works out to about 190 EU per liter. You do have to use a Dangote distillus and not overclock anything. But most of the recipes are in an LCR, so you can get perfect overclocks, which is energetically the same as not overclocking, but it's faster. And again, I do the same thing that I did before. I'm just looking at the total energy that goes into making grade 3 water divided by the expected amount of grade 3 water that I'm going to get out. And similar to grade 2 water, it turns out that supplying the maximum amount of polyaluminium chloride gets you the best result. Grade 3 water is pretty expensive. It's almost 1 million EU for 1 liter. This is of course from scratch, so starting at nothing, it will cost you 1 million EU to make 1 liter of grade 3 water. And I'll have to supply 1 million polyaluminium chloride and recycle it within 2 minutes. So I haven't checked how fast the recipes are. I don't know how many machines I'm going to need to keep up with that, but I'm going to have to keep up with that. Grade 4 water is difficult to estimate because there's a bit of random variation, and dealing with that random variation has an EU cost, but it's not significant. So I just neglected it completely, and I'm just looking at the energy for grade 4 water. And this actually has a 100% success chance if you set this up correctly, so no probability here. I'll come back to that once I actually set that up. But for now, we're going to be doing grade 3 water, and I need to make 1 million polyaluminium chloride. Here is the flocculation waste liquid recycling setup. I put it on a subnet. It actually doesn't see anything on the mainnet. The only link here is for power. So I use the subnet to route things around, and basically what happens here is I generate 1 million flocculation waste liquid in this output hatch that goes into this Dangote, where it's distilled into aluminium dust, oxygen, and hydrochloric acid. The aluminium dust goes into this chemical reactor, where it's combined with sodium hydroxide to make sodium aluminate. That is stored in this next chem reactor in the input bus, where it's mixed with water, and we get the sodium hydroxide back, so that goes back. And also we get aluminium hydroxide, and that goes into this quad setup. This quad combines the aluminium hydroxide with hydrochloric acid, and that gets us the polyaluminium chloride again, and that goes back into the input over here. We also get a bit of hydrogen and oxygen. I say a bit, it's actually quite a lot. But the main thing here is that everything happens within the 2-minute window of a processing cycle. At the end of a cycle, it'll generate 1 million waste liquid, and by the end of the next cycle, the ongoing cycle, all of the PAC will make it back into the input hatch in time. And you can actually use the portable scanner and scan the multi-block, and it tells you how much is used in this cycle. And it's really, really punishing if you don't do a multiple of 100,000. When I was scanning before for a second, it was at 999,000, and it had a 0.1% chance of success. You need to be quite precise with the amount you put in. So all of these machines are running at LUV. Once I get ZPM hatches, I could reduce this down to a single LCR if I wanted, and that would be able to keep up. But yeah, we now have grade 3 water. Thank you for watching this episode of the HamCorp Training Manual. In the next episode, we will craft the first few ZPM energy hatches, which will allow us to finally make the XL supercritical turbines. And then I can let the Waterline run constantly for basically free. After that, we will continue with core progression, which likely means I will have to continue upgrading my rocket. See you next time.